Now, one of the interesting things about the multiverse that I want to stress is that actually there's an interesting way in which it might be testable. So here's an example of how it might be testable. Now, my experience over the last couple of weeks, I've just been giving some talks around the US, is that this is the slide at which some people get lost. So you can do this, people get this, but you're going to have to pay attention, all right? Or if you don't, you can at least enjoy this picture of Fry from Futurama. This is called Revenge of the Boltzmann Brains. And what we want to do is just treat the multiverse like it's any other scientific theory. So what does it predict?
Did we just get really, 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 really lucky? No. The probabilities involved are so ridiculously remote as to put the fine-tuning well beyond the reach of chance. So, in an effort to keep this option alive, some have gone beyond empirical science and opted for a more speculative approach, known as the multiverse. They imagine a universe generator that cranks out such a vast number of universes that, odds are, life-permitting universes will eventually pop out. However, there's no scientific evidence for the existence of this multiverse. It cannot be detected, observed, measured, or proved. And the universe generator itself would require an enormous amount of fine-tuning. Furthermore, small patches of order are far more probable than big ones. So the most probable observable universe would be a small one, inhabited by a single, simple observer. But what we actually observe is the very thing that we should least expect: a vast, spectacularly complex, highly ordered universe, inhabited by billions of other observers.
So it turns out that nearly all initial conditions of the Big Bang would have resulted in a lifeless black hole universe. Roger Penrose is, I think, the first one that computed these odds, but many other people have confirmed them. But he puts the odds against life at about 1 in 10 to the power of 10 to the 123rd. So not just 1 in 10 to the 123rd, but 1 in 10 to the power of 10 to the 123rd. So writing out that number in normal form, like if you just included all the zeros, you wouldn't have enough particles in the universe for every zero in that number. And he considers whether the multiverse might help with this, but he says that it's actually worse than useless in explaining the anthropic fine-tuning for this parameter anyway, because it predicts exponentially more, exponentially smaller universes. So multiverse predictions are so vastly different than what we find in our universe that he views that as reason to consider multiverse proposals and explaining this worse than useless. So he finds it very surprising on multiverse theory on general grounds that you would have a life-permitting universe that would be of this large size. One way to think of it, and by the way, Sean Carroll's written on this too, and he also agrees that the multiverse and an anthropic multiverse explanation fails for the low entropy condition of the universe. And you can think of it by thinking in terms of what do we need for life? We certainly don't need anything more than our solar system. We could survive quite well with just the sun and the planets. Maybe you don't even need all the planets.
We read this quote by Roger Penrose, first of all. Do we really need the whole observable universe in order that sentient life can come about? This seems unlikely. Let us be generous and ask that a region of radius 1/10 of the observable universe must resemble the universe that we know. But we do not care about what happens outside that radius. We can estimate how much more frequently the Creator comes across the smaller than the larger regions. The figure is no better than 10 to the 10 to the 123rd. Okay, so you see that an incredible extravagance it was in terms of probability for the Creator to bother to produce this extra distant part of the universe that we don't actually need for our existence. In other words, if we live in a multiverse generated by a process like chaotic inflation, then for every observer who observes a universe of our size, there are 10 to the 10 to the 123rd power who observe a universe that is just 10 times smaller. Okay, so that means that the universe, if we really did arise from chaotic inflation, or just a quantum fluctuation of the vacuum, then the universe that we see beyond our region of space, or say years, million light years, is not really there. It's an illusion.
But if we are just a randomly ordered member of this ensemble, such that the probability is that somewhere these constants would be finely tuned, then things that are even less improbable ought also to be appearing conjointly. And yet we see a rationally ordered universe, and that cries out for some sort of explanation. In addition to that, a much smaller inflationary patch would be sufficient for our existence, rather than the large universe we see. And it is overwhelmingly more probable that if we were just a random member of a world ensemble, we should be observing a much smaller inflationary patch than what we do in fact observe. And I think this is really the Achilles heel in this multiverse hypothesis, that if we were just a member of a multiverse, randomly ordered, then it is overwhelmingly more probable we ought to be seeing a very different kind of universe than the rationally ordered world that we do in fact see.
The minimal universe that could support life would be what we would expect to be in, and the fact that we're in a pretty extravagant universe is against that.
This point has been made very forcefully by Roger Penrose of Oxford University. What Penrose points out is it is incomprehensibly more probable that our solar system would just instantaneously form through the random collision of particles than that a finely tuned universe would exist. What that means is that there are far more universes in this multiverse in which observers form just by the random collision of particles than finely tuned worlds.
I think it was Roger Penrose as well who was saying, well, it's more probable that the entire solar system would come into existence randomly out of the collision of some particles than this fine tuning. And I just wanted to know,
that's a very important objection. So this centers around the initial mass distribution of energy in the universe. And here's an example: if monkeys were typing on a typewriter, let's say, it'd be vastly, and you had all the monkeys you wanted, and eventually they would produce a meaningful sentence and occasionally a meaningful paragraph. And if you had enough monkeys, occasionally Shakespeare. But it would be vastly more probable for them to produce a meaningful sentence or a meaningful paragraph than the whole Shakespeare. It's like, or if you had 100 coins lined up and you shook them, and let's say it'd be vastly more probable to get, let's say, 5 coins in a row of heads somewhere. In fact, that'd be near probability 1 for that to happen, than for them all to come up heads. So the idea is if the universe, the arrangement of mass energy were just at random, it'd be vastly more likely for a small region of order to occur, enough for intelligent beings like us to pop into existence.
You take this to the extreme, you have what are called Boltzmann brains. Take it to the extreme, we can have a universe. We can have a universe pop out of a quantum fluctuation that contains one brain. Boltzmann brains are by far the most common observers in the multiverse, given their small size. Smaller the object, smaller the universe, the more probable it is. So it's far more probable to occur in a multiverse than for a Boltzmann brain to occur in a multiverse than our vast fine-tuned universe with its long history.
And so it'd be vastly more likely for this brain to form just by a random fluctuation and suddenly have consciousness and then pop out of existence than for us to experience a world where we're interacting with other people.
So if we were just a random member of a multiverse, we ought to be observing an island of order no bigger than our solar system, because that's incomprehensibly more probable than a finely tuned universe. In fact, the most probable observable universe would be a universe in which a single brain fluctuates into existence out of the quantum vacuum and observes its otherwise empty world. So if we were just a random member of a multiverse, we ought to be having observations like that. And since we don't, that strongly disconfirms the multiverse hypothesis.
So the most likely answer to the question, what kind of thing are you when you go around your universe, is I'm just a brain surrounded by total thermal equilibrium, total chaos. Right? So the problem with that is it's wrong. This is not the brain in a vat, am I in the matrix philosophical thought experiment? How do I know I'm not just a brain? This is just, you got a theory, makes a prediction. What kind of thing are you when I go around and ask in the universe? And Boltzmann's multiverse says that most people should answer, I'm just a brain in a vat. So the fact that we're not that kind of thing is then evidence against the theory. The theory leads us to expect something, and that expectation is wrong, and so the theory is probably false. So that's called the Boltzmann brain problem. It's a way in which the multiverse could actually be wrong.
And so the fact that we're in a world where we can interact with other people, that would be expected under theism. God's not going to produce these isolated brains that pop into existence. But what would be expected under atheism is this is vastly more probable, just like in the monkeys typing on a typewriter, is simply this what's called a Boltzmann brain. So it has a huge difficulty in explaining the fine-tuning.
I'd say it just goes nowhere. You don't have to go any further than to say you have to believe in illusionism, and that you're the only real brain, you're the only real mind in this room. That's the only real observer.
Roger Penrose at Oxford University, according to him, the vast majority of arrangements of matter in our early universe result in universes dominated by black holes, and that's obviously not conducive to life. And according to his math, the ratio of life-favoring universes to life-disfavoring universes is 1 in 10 raised to the 10 raised to the 123rd power, which obviously has more zeros after the 1 than subatomic particles in the known universe. Do you think that's a strong argument as a case of fine-tuning?
So, yeah, the initial entropy of our universe, I think, is a particularly strong case. It's sort of dawning on me how much stronger it is than a lot of the other ones. The reason is that it's the one that really hits the Boltzmann brain problem hard. It got that was the sort of explanation of how do we get the low entropy, the order in our universe. You just wait around until it happens by accident. The problem is you'll only get as much as you need, and you're probably just a brain in a vat. Right, that's a problem. That argument is basically the same as what it happened to Boltzmann. All that Penrose is doing is applying the same thing to the very earliest stages in our universe and an understanding of what the ultimate high entropy state of the universe would be, which is just totally filled with black holes. And the numbers you get out are ridiculous. They are extraordinary.
But I think if you can tweak some parameters, if you can do some fine-tuning, basically, you can get around the Boltzmann brain problem. But again, the problem is if you have to do fine-tuning to avoid this problem, then have you really removed fine-tuning? I would argue not. Right.
No, that's very much the case. And, Sean Carroll, who's done quite a bit of work and, speaks fairly popularly on things, he argues that Boltzmann brains are, I think the term he uses is cognitively unstable. But what I find interesting is his solution to that. So what he does is he looks at the different scenarios we have out there, and he applies a criteria that any universe that produces Boltzmann brains isn't a good model. Well, that's designing things. It's saying, all right, in this scenario, or of the possible outcomes, we're eliminating the ones where you got Boltzmann brains. Well, I could also go and say in my models out here, I'm going to eliminate all the possibilities where carbon doesn't exist. That's how you end up with, that's how we ended up with some of our fine-tuning arguments for the laws of physics. Well, to me, it seems like all he's doing is just designing things so that we don't get those unworkable scenarios. But that's still design. Or that's fine-tuning, design, purpose, whatever you want to call it, it's still being applied there. So, as I've looked at this, a lot of times, we'd have this particular design argument or this particular argument for fine tuning, and we'd kind of squeeze on that, and scientists might solve that, but that design ends up popping up somewhere else. It's hard to put that into an argument or quantify it or stuff, but it seems like that happens very regularly, and I can give you numerous examples where that's happened.
We could have existed in a universe that was vastly less discoverable. And you can move the constants around. We could exist in a universe that you couldn't get beyond the Stone Age because you couldn't build open wood fires, that microscopes did not have the resolving power they do. They have far less, in which a host of other factors weren't right for the development of science and technology. So when you bring that in, a fine-tuning for not only life, our kind of life, but that we can actually come to know about the universe, discover its structure, then you get something beyond any ability of an observer selection effect to account for.
Carroll admits this in his article. He admits that the fine-tuning is far, far in excess of what would be necessary to sustain observers, and that therefore you can't really explain the fine-tuning simply as a self-selection effect of observers. So it's very odd. He likes the multiverse hypothesis, and he doesn't come out and admit that it's inadequate, but nevertheless, he does give you here the raw materials of an objection pressed by people like Penrose that show that this multiverse hypothesis is not going to work as an explanation of fine-tuning.
What kind of conclusions does he draw from that there is this excessive fine-tuning?
Well, he doesn't come right out and say, this shows that the world ensemble or multiverse hypothesis won't work. But what he'll do is he'll then go to alternative 4, and he'll pull a move that I call so's your old man. That is to say, he'll say, well, but the same objection applies to the designer hypothesis. The world exhibits far more fine-tuning, far more design than is necessary. So why did God or the designer so finely tune the universe
beyond what is necessary?
Yes, beyond what is necessary in order for observers to exist. So he doesn't have an answer to this objection against number 3, but he wants to simply say, well, but it also applies to you proponents of number 4.
So's your old man.
Yeah. The problem is, Kevin, it doesn't apply to number 4 in the same way. The hypothesis of intelligent design doesn't depend upon a self-selection effect for observers. So while this consideration is a potent objection to saying, well, fine-tuning is just the result of a self-selection effect of observers, saying that the universe is more exquisitely fine-tuned than is absolutely necessary doesn't do anything to subvert the hypothesis of intelligent design. In fact, what it would show is that the designer is far more intelligent than even is necessary to make observers.